Hello YouTube, it's Nick Wynn back at it again with another tutorial. Today's tutorial will be going through Optuna. Optuna is a package that allows you to hyperparameter tune your model. You might be thinking you've heard of this before. It sometimes is called grid search, sometimes it's called randomized search, but let me tell you that Optuna can be faster than grid search and can be more accurate than your randomized search. Today's data set is baseball, and we will be trying to classify pitch types. Some pitch types are really fast, some pitch types have a lot of movement. That's what differentiates a fastball from a slider and a slider from a curveball. It's really difficult to know what pitch type is which unless you watch a lot of baseball. So let's use machine learning in order to classify our pitch types. If you're wondering how to get a copy of this notebook, you could actually click a link below in the description and you'll be taken to this exact notebook. It might not be exactly in the coding language that you are experienced with, but if you are using Python, then this will speak to you, especially all of the machine learning and the Optuna package stuff. If you are in R, or if you're in Rust, or if you're in Julia, all the machine learning here is pretty similar conceptually. I'm not too sure if Optuna is available in some of these other languages, but if it is, please link it below in the comments and just let people know where you could find Optuna, where it's available today. Since we're using Google Collab, we're gonna have to install some packages since they're not installed already in Google Collab. We're gonna install PyBaseball in order to get our data, and we're also going to install Optuna since we're going to be using Optuna in this video. And in the next cell here, you could actually see us importing our libraries. You're seeing PyBaseball coming in. You're seeing pandas coming in. You could also see us bringing some machine learning packages. In this case, we're going to be using scikit-learn for all of our machine learning. You could also see us bringing in Optuna, as well as some data visualization packages. For these 4 lines of code right here, we are actually just going to be looking at the 2022 season and only 3 months of data. So this is from the beginning of April to really it's the end of June, but all the way up to the 1st of July. So maybe a little more than 3 months of data, but this should be a lot of data. We should be able to create a pretty good model with this, and we shouldn't have any sample size issues. Now, if this is too much data for you, feel free to modify the date here. You could use 1 month of data, you could use a week of data. There's a lot of pitches in a week of data, so feel free to use a smaller set of data if you can't necessarily use all 3 months of this data because of your computer. If you're in Google Colab, this works completely fine. You will be able to get all 3 months of data in your Google Colab environment. The next thing we do is we drop null pitch types. You might be wondering, what's a null pitch type? I thought all these different pitch types were going to have names like slider, fastball, curveball, knuckleball. Well, they do, but sometimes the tracking of the data is inconsistent and imprecise, so sometimes they can't tag the pitch with something like a slider or a fastball or a curveball because it just isn't able to tag it due to the data quality or due to something with their camera system. So we're going to just drop the subset pitch type, and we're going to drop anything that's null. That way we have only pitch types that were tagged. Also, you'll see that we're going to reset the index. Usually I don't recommend doing this because of how powerful the pandas index is. And if you've seen some of my React content, you might see me talking about how powerful the pandas index is and why you should maintain it at all costs. But in this case, the reason we do it is because they duplicate the same index, in this case 92 times, and the reason it's 92 times is because they're downloading the data in 92 segments, so we get a lot of duplicate indices. In order to have unique indices, we're going to just reset the index here. At the end of it, when we're printing our data, these pitches have happened in the past. We shouldn't really have differences in the number of rows of data, so you should be getting something around 346,000 rows. Before we do some exploratory analysis, let's cut down our data set so we're only looking at 10,000, that we don't have to plot all 300,000 pitches, and that's going to take a long time. So let's look at a subset of our data, and let's also make it a little more specific. Let's only look at fastballs, sliders, curveballs, and changeups. And let's also only look at right-handed pitchers throwing. So let's get 10,000 rows that meet these conditions. I'm doing this all through pandas, and let's save that as a variable called dfplt. I like using this as a shorthand for my plotting data frame. You're gonna see a lot of that if you follow along with my notebooks or on my streams. The first pitch type plot that we have here is break. Break is just the difference between actual physics and ideal physics. When a pitch type comes in a vacuum, it should just be in the straightest line. But on Earth, with gravity, with air resistance, you'll see breaking or actual physics happening. That is not ideal physics. So this is really just the actual physics of the ball on Earth compared to our ideal physics in a vacuum. And that's why we see things like changeups going more towards the left side, sliders and curveballs producing more break to the right, and fastballs maybe producing more break in upward fashion. So let's take a look at how we plotted that plot. We use Seaborn's scatter plot function here, and we're bringing in that data set that was the subset of the 10,000 pitches we selected, and then we're plotting PFX-X on the x-axis, PFX-Z on the y-axis. This is the break horizontally and vertically. We're also creating the hue, or in this case, the colors or the categories by pitch type, and that's what's giving us the red, green, blue, and orange colors of our pitch types on the graph. We then use a D-spline just to make the plot look a little more aesthetically pleasing. We put a title over it because we're talking about pitch types over break. And then we have this show here just to plot, to actually show the plot. The next plot we have is pitch types by speed. Obviously, the fastest pitch types here are the fastballs. You also see a lot of fast sliders, and you also see a lot of fast changeups here, and you'll also see curveballs end up being a slower pitch type. For this plot, we're using a box plot. Again, using that subset of data, plotting X as release speed, and we're using pitch type as our y-axis. You might be wondering, well, that's not what it looks like. It looks more like that, but flipped on its side. That's exactly what this next line is. We're orienting the plot towards the horizontal plane. That way, all of this is flipped on its side, and we could read the pitch types, and our values are on the x-axis now. Similarly, we could actually talk about spin rate. Notice how sliders and curveballs end up having a higher spin rate than our fastballs and our changeups. Again, we could plot this with box plots the same way. This time we're going to use spin rate instead of release speed, and we're still going to flip this horizontally to show our distribution and our values on the x-axis and our pitch types on our y-axis. So overall, just looking at this data visually, we can actually see that you can differentiate pitch types by a few different ways. Break looks like it's one of the most important features for pitch type. We also have spin, and we also have velocity. If you applied for my data scientist role for the Reds in 2022, then you might have seen something similar to this in the technical assessments. Now that we've explored our data and we kind of have an idea of the features we want to use, we know we want to use break, we know we want to use velocity, we know we want to use spin rate. Let's try to feature engineer some things into our data set. That way our model can pick up on these features and accurately predict what pitch type is being thrown. The first thing I want to do is tag whether or not a pitcher is left-handed or right-handed. You might be wondering, why does that matter? Well, when the pitch comes out of the right hand and you might be throwing it with some sort of spin, that spin might be, say, counterclockwise. Whereas if you're right-handed and you throw with another type of spin, that spin might be clockwise. This will produce two different break profiles. In order for the model to know whether or not this pitch type is supposed to be a changeup versus a slider, we're going to want to tag whether or not this is a left-handed pitcher or a right-handed pitcher. So let's make this using pandas, using conditional filtering. Let's filter for all left-handed pitchers, and if they're lefty, let's just say 1. Now let's go and define the features we're going to use in our model. The first thing I want to do is leave in some ID features so I can actually look through what players are doing what pitch types are real. That way when I look at my end result, I have some IDs, some things that my model's not training on, but are helping me navigate and explore my results at the very end. The next two things are going to be based around our machine learning model. The first thing is something I call feats, which is just short for features. Again, we're going to say whether or not they're left-handed. We're going to use speed of the pitch. We're going to use the spin rate of the pitch. And we're going to use PFX-X and PFF-Z. And PFX, X and Z are the break features. We're going to be looking at target pitch type code. Now, you might be wondering, well, we don't have pitch type code yet. That's true, this is typically faux pas encoding, but I wanted to keep all the modeling things conceptually together, so we end up doing target equals pitch type code here. The most appropriate way to have this line is actually to have it after we make pitch type code here on line 14. But for now, let's just keep it here. That way, the YouTube video sounds nice and smooth. So let's now make our subset of data. And the way we want to do that is actually to drop any null values or any values that do not exist in this data set because of maybe bad tagging, bad data collection, just like how pitch types didn't exist in the original data set. Some pitch types didn't exist in the original data set. Some speeds, some breaks might just not exist because of artifacts in the data collection process. So let's make sure we only have rows of data that are completely filled with our ID features, our features for our modeling, and our target. Let's also eliminate one pitch type that's extremely rare these days. Let's take out the knuckleball from our data set. There aren't many knuckleballs thrown. And because there's so few of them, sometimes when you run this data set, run through this notebook with knuckleballs in there, you might actually get big errors and you can't actually complete the model training. So let's just take out knuckleballs simply because they're not thrown that often anymore. Now let's turn our pitch types into numerical values. I'm going to use a built-in pandas function here called asType. And we're going to use the category string here. Pandas knows that we're trying to change this column, pitch type, to the type category. Now, category is actually a built-in pandas method where you're able to turn an entire column into categorical features. When you turn something into a categorical feature, a categorical column, you're actually able to access something called codes. And codes gives a unique value to each of the labels in your column. So in this case, I want a unique value for each of the pitch types. This is a great way to do it without having to duplicate any IDs. This works seamlessly across different pandas data frames, and this will work very seamlessly when you run this notebook, if you run this notebook on your own. And of course, let's save this as a variable in our data frame called pitch type code. Finally, for our machine learning data set, you've seen this before if you've looked at other machine learning tutorials. We're doing it here. We're splitting our data into a train set and into a test set. We're going to use pandas for this. Some people use scikit-learn. Some people have other packages they use for splitting into train set and test set. I'm just going to use pandas to do this. There might be more efficient ways to do this, but this is a pure pandas way to do this that I'm very comfortable with. I use this all the time. If you're comfortable with scikit-learn train test split, that's also a good way to do this. Let's take 50,000 samples from the subset of data, and let's call that the test set. Now let's make our train set. And the way we're going to do it is we're going to use the loc function here in pandas. Let's subset our data and let's look for any index value that's in the test data set that we just made. When we look for that, we would normally get all of the test index values. So let's use this tilde in the beginning to say, don't look for any of those numbers. So ultimately what this is saying is, if the index value in this data set matches any of the index values in the test set, don't include that in this data set. One caveat to this is a really important pro tip if you do it this way, which is why it's kind of do it at your own risk. When you are looking for the test index, make sure you put .values at the end. If you don't, you actually will crash your notebook. And if you don't believe me, feel free to try it. Your notebook is guaranteed to crash. Also, we're gonna use that sampling function again. In this case, we're gonna get 100,000 pitches randomly from a subset of data. So at the end, we're gonna have a test set that's 50,000 different pitches. And then we're gonna have a train set that has 100,000 different pitches, and they do not match any of the pitches from the test data set. In this next cell, what we're really doing is we're preparing to map pitch names back to the numerical values. So remember, we use that categorical codes line. The reason we do that is so we can get numerical values, and that's because our machine learning model is looking for numbers. It's not looking for strings or alpha characters, right? In order to translate this back from pitch type codes back to the pitch type names, we're gonna need some sort of mapping system. So this is a pretty complex pandas mapping system. What I'm doing is I'm taking the subset of data, I'm looking for just the pitch type and the pitch type code, and I'm dropping all the duplicates. So we're only getting one line for every pitch type and pitch type code. In the next line here, we're actually gonna set the index to the code that's actually setting the index to the number of values. And the reason we're doing this is because when we're trying to rename our numerical values back to our pitch type names, it's gonna look for the keys in a dictionary and then apply the values in that dictionary. If you're still a little confused in Python and you're like, well, I don't know what a key is, I don't know what a value is, I don't know what a dictionary is, you might be a little too deep into this notebook. You might want to check out some of my friends who do go over a lot of introductory material. So you should check out some of my friends over here. I believe they're over here over here, I don't know, over that way somewhere. And in this last line, it's a little clunky, and there's definitely a better way to write this. And if you know a better way to write this, feel free to post in the comments below. But we're going to convert this to a dictionary, and we're only going to look inside of the pitch type key. This is going to give us access to the key values that we want to match. And so let's save this all to map pitch types, because that's ultimately what we're going to do. We're going to map this back to our numerical values when we produce all of our results. We also list all the pitch type names, just the unique pitch type names. This is going to help us sift through some of our data later on when we're doing some modeling. And just so we can show everyone what the pitch types and the pitch type codes are, I end up sorting through the table. And here you can see on the left all these different pitch types. You can see changeups, you can see fastballs in there, you can see sliders in there, and you can see all the different values. In this case, in my data set, I have 11. Remember, Python is 0 index, so there are 11 different pitch types. If you're using a larger data set, you actually might see more pitch types. If you're using a smaller data set, you might see less. All right, now we're gonna get to the machine learning stuff. You've probably seen this before. You've gone through some machine learning tutorials. We're gonna start off pretty easy, and we're just gonna use a logistic regression to classify our pitch types. We're gonna set our logistic regression to this variable called log R, short for logistic regression. Let's fit our model with our training data. We're gonna use our features that we define and our target. We're gonna predict the probabilities of all the pitch types, and we're gonna put that in a pandas data frame. When we do that, we're also gonna set the index to the test data set. You might be wondering like, well, I never do that and I'm fine. Well, you're fine until you're not. Setting an index explicitly really saves you from all the times where you're joining your predictions from a NumPy array back to your pandas array, and the index doesn't match up. It's a really bad way to start off a week if you come in and you have a bunch of null results when really you shouldn't have. Setting your index is a really good way to avoid that. I do it every time. You can also see that we're renaming our columns in this case, And notice how we're using that map pitch types variable we defined earlier in the notebook. This is just going to allow us to talk about things in terms of the pitch types and not in terms of the numerical representation of the pitch type. After all of that, we're actually going to concatenate this back to our test set. You might have seen in some notebooks or maybe on my streams before that I used to use append, but in newer versions of pandas, they're actually going to deprecate append in favor of pandas concatenate. So I am now going to be using pandas concat or concatenate for the rest of my tutorials and for all my streams. So if you saw maybe a tutorial before where I use append or I talked on stream about append, I'm not doing that anymore. Finally, we're actually going to get the predicted pitch type. The way we're going to do that is actually going through all the pitch types. We defined this earlier when we were defining our mapping. And when we do that, we're actually going to look for the maximum probability, but instead of getting the max probability, we're actually going to get the IDX or index max. So rather than saying, oh, this thing has 99% probability of being a fastball, it's going to say, oh, the highest probability was a fastball column. And so let's take the column name and use that as a label. And in order to do that, make sure that you're splitting through axis equals 1. That way you do it row-wise and not column-wise. One thing I really like doing after I do anything with machine learning and predicting anything and joining it back to my test set is just checking the data quality. So I'm just gonna sample 10 rows here just to see how the predictions came out. And you can see that we have all of our different pitch types across the top. And you can see all these values. These values are actually different probabilities. You can see that in this case, this particular row is being classified as a slider, 54%. Over here, there's a 6% chance of this being a curveball, so on and so forth. And you can see all the way at the end here, pitch type prediction is whatever the highest likelihood was of that row. So in this case, it's looking for four-seam fastball. You can see here that the four-seam fastball came out as a 46% likelihood. Rather than taking the max, we took the IDX max. So the label for this column is FF, or four-seam fastball, and that's why this says FF instead of 0.465. Your sample data might look a little different than mine simply because I'm randomly sampling over 10 rows, but if you want to take a look at exactly these rows, here are the index values right here. And again, you might not have these exact index values in your data set because of how we created our train test split. Okay, now we've created our model, we've created our predictions. What's the last thing we need to do? Let's see how good the model was. We actually see using accuracy, which is whether or not we're labeling the pitch type correctly, we're 54% accurate, which is pretty good given how there's 12 different pitch types. So being 50% is definitely greater than chance here, greater than random guessing. We also see that our log loss is 5.15, and I'm not too sure if 5.15 is good or if it's bad yet, but I'm sure we're gonna find out very soon when we start modeling other things. So given the fact that some of our features are non-linear, like our break feature, it isn't like as break increases, the pitch types also end up being fastballs. Because we have non-linear features, sometimes these linear models have a hard time trying to learn the rules of a particular feature. So sometimes we want to switch off of a linear model in favor of a non-linear model because they're going to handle some of these interactions between variables better than the linear model does. We're going to use random forest because random forest is a non-linear model, it makes no linear assumptions, and hopefully it's going to be able to handle some of these features like is lefty or break better, and hopefully that improves accuracy and decreases loss. First thing we do here is we're going to drop all of the pitch type columns from our test set. This is so we're just cleaning our plate of any of the old predictions. We don't want any of the old predictions in there. Let's just start off with a new model and new predictions. Now, if you want to rename your predictions so you could keep all your predictions in one data frame, you could do that. It's an easy change, and that way you wouldn't have to drop any of your features. I'm just doing this way out of convenience and really out of laziness. This next chunk of code is using the random forest classifier instead of the logistic regression. You're going to see that all of the code is essentially the same, except instead of using log r as our variable type, I'm using rf because we're using a random forest model. And of course, because we're using a random forest model, we're using random forest classifier instead of logistic regression. You can see that all right here. The rest of this is pretty much identical to the previous model train cell. The only thing really different is the RF here. Again, for data quality, we're gonna look at 10 random rows, and you can see that we replaced all of our pitch type predictions. Now we have more definitive predictions, and yes, our pitch type predictions are based off of the highest likelihood. Like in this particular row, we're classifying this as a 4-seam fastball at 98%. Of course, let's check out our model metrics, and we can actually see here that our model's accuracy is way better at 84%. That is a gigantic improvement over 55%. But you can actually see our loss is way worse. And you might be wondering, well, the loss is worse, but the accuracy is better. Is this really a better model? Well, the reason is because it is classifying pitches so strongly. Remember, this pitch type that was classified as a fastball at 98%, you're getting a lot of classifications where they're putting a lot of eggs in one basket. So rather than hedging and having a lot of predictions near the average, we're actually getting a lot more accuracy at the cost of being wrong larger. So with more, when we're wrong, we're really wrong, but when we're right, we're 84.4% accurate. All right, so we've gone through a linear model, we've gone through a random forest model. Finally, the moment you've been waiting for, how do we use Optuna? First thing we gotta do is, again, we're gonna drop those predictions we had before, and then we're gonna define our Optuna function. So Optuna needs a function in order to run over all of its different parameter combinations, just like any grid search or any randomized search. But because it does it smart, you only need to define a range of values. So for us, we're gonna use our n estimators in our random forest classifier, and let's suggest an integer range of 10 estimators all the way through 500. And it's going to figure out in some smart way what the best, most optimal n estimators are. Also, we're gonna tune over our max features. Typically, and for most models, you tend to set this as auto, but let's just do it manually, and we're gonna look through our two different categorical values, square root and log base 2. Once you've set your n estimators and max features, Optuna ranges, we're just going to actually code the same model type as we did before. So we're gonna set a random forest classifier up, but in this case, we're gonna say n estimators equals our n estimators we defined from our Optuna, and our max features, just like the max features defined from our Optuna line here. The rest of this function is just machine learning like we've just discussed. We're gonna fit our model with our training data set. We're going to produce a temporary data frame with our predictions, and then ultimately we're going to create an accuracy score, and we're going to return that accuracy score. This is just like the steps we did above for the logistic regression and also for the random forest. It's just all slammed into this one function now. So after you set this function up, we're gonna set up the study, which is what Optuna uses. They call these things like studies and trials and experiments. Basically, it's like its own hyperparameter tuning lab. So let's set up a study and use that using this line, optuna.createStudy. And it asks you for one thing, and that's what's the direction of the metric that you're using. And in this case, because we're using accuracy, we're going to use the direction maximum. If you're going to use log loss or something like root mean squared error, you're going to want direction minimum. After we set up our study, we're going to optimize and we're going to insert our function we made. In this case, I called it tune, and we're going to run this over 3 trials. You can run this over as many trials as you want, and actually Optuna has this nifty feature where if you're running over a lot of trials, you could actually set a timer in seconds to say, after X amount of time has expired, let's just call it quits. So there's a lot of different time control and trial limits that you could put on Optuna that other packages might not have. So in this case, we're using 3 trials just for the sake of this tutorial. You can use more if you want. And we see that after our 3 trials, our best parameters are 305 estimators with a max features categorical value of log 2. And you can see here in the output, in the verbose output here, that trial 1 was the most accurate with 84.6% accuracy. So it's going to use this run, trial 1, as the best parameters. Now, if you use more trials, you might have a different accuracy, and you definitely will have different sets of new estimators and maybe a different max features value. At the end of the day, the more you can train through this, the more accurate you're going to find your model being. After we know what our n estimators and our max features are, it's just like the random forest cell before, except we're just plugging that into a random forest classifier at the beginning. We're going to set our n estimators to what the best parameters from our study were, and we're going to set our max features, again, to what our study recommends as our best parameters. From here, it's the same as the logistic regression, it's the same as the random forest, is the exact same. We're just going to fit the model, we're going to predict, and we're going to find the IDX max. That way we could say what pitch type was this trying to classify as. And of course, the accuracy as to what we're getting isn't actually that much better. I got 84.5%. That's only a tenth of an improvement from 84.4%. Really negligible. And our loss is actually slightly better at 30.88. In this case, that's beating our 31.73. So we do improve in loss a little, we do improve in accuracy a little. If you use a model type, that's better. Or if you use random forest and you could train on more features in your Optuna space, you're probably going to beat me. Post in the comments below whether or not you were able to beat my accuracy or my loss score. And that's really all for Optuna. So if you've made it this far, you should have been able to go from the beginning of my notebook, bringing in the data, making some new features and adjusting some features to fit our models, going through a linear model and a non-linear model in order to predict pitch types, and finally using Optuna in order to optimize your random forest model to get even better accuracy and lower loss in your model. If you like this walkthrough, please like and subscribe. Also, check out my other content when I'm talking about tech news. You could also check out some of my game shows. I run a data science game show called Slice, and I also run a data visualization game show called VizBuzz. And coming up in 2023 is my new game show called Nick Wan Versus, where all the people in my community try to challenge me to a speed data science competition on Kaggle. If you're interested in learning more about that, you should follow the Twitch stream. The link is down below. If you're interested in watching any of this content live, I do this every night, Monday through Thursdays on my Twitch channel, also in the link below. Check out my channel for more tutorial content and also a lot more data science and data science related content. I'll see you next time. How do I get a GF as a CS major? Change majors.
Bruh.